All right, welcome back. So this is an ALEKS topic that was requested, so thank you for the request. This topic is called predicting relative boiling point elevations and freezing point depressions. So this is a really, it's actually quite a complex topic. I think a lot of times when these ALEKS topics just sort of have you rank these things, they can be actually a lot more complicated than you might think. So there's a lot going on in this, so we'll go ahead and get into it. I'm going to do two different examples of this problem to just expose us to a few different ways that we're going to be asking this question and get some extra practice with this Van't Hoff factor I, but we'll talk more about that in a second. So the first thing I guess we should talk about is these equations for the freezing point depression and the boiling point elevation and really what they mean. So we're talking about a colligative property. Colligative properties are really important in chemistry, I think. And what's important for colligative properties is not the identity of what the solute is. It doesn't matter that it's sucrose versus glucose. What's really important is the count, the number of glucose or sucrose or hydrochloric acid atoms or ions or molecules, the count of how many things basically there are in your dissolved in your solution. And that's sort of how this Van't Hoff factor comes in. So if we look at these equations, the change in the freezing point, and the freezing point is always going to get lower. So as I put a solute in, it's actually going to make the freezing point lower. So the freezing point will always get lower. It's called freezing point depression. And the boiling point will always get higher, boiling point elevation. So if I look at this equation here, the Kf is going to be a constant for water. And we're not actually going to do the we could, but I'm not actually going to do the calculations. I'm going to think about this conceptually. But we could do the calculations. So the Kf, we just looked that up for water. It's going to be constant. The Kb, again, we're going to look that up for our solvent, which in this case is always water. The M is the molality, and molality is going to be a measure of how many moles of substance you have. So really, we can sort of do a ranking based off of, well, I know this is a constant, what's my number of moles of each of my solutes, and think about what effect that's going to have. And then I is the Van't Hoff factor. So Van't Hoff factor. And the definition of I is how many sort of particles or pieces your solute is going to break into. So if it's something that's molecular, like sucrose or glucose, these are molecular compounds. When you dissolve them in water, they're going to stay together. That whole sucrose molecule is going to be floating around in the solution as one molecule. Whereas if I look at something like HCl or other ionic compounds, they're going to break into pieces, right? They're going to break into multiple different ions. So they're going to have a different Van't Hoff factor. So for HCl, the Van't Hoff factor I is actually going to be equal to 2 because it's going to break into two pieces. For sucrose and glucose, the Van't Hoff factor is 1 for both of those because both of those are molecular compounds. They're not going to break into pieces essentially. So another piece that we're going to have to take into account essentially. Okay, so when we're looking at this, pure water is always going to be the I've got it. It's going to have the highest. So 4 is the highest. So this is, I'm not sure how we can show this clearly. So the pure water is always going to be the highest freezing point. So 4, I guess it says it up here, and 1 is the lowest. So 1 equals lowest, and 4 equals highest. So if it's boiling point elevation, then the lowest boiling point is always going to be the pure water because all of these other, as I add these solutes in, it's going to make the boiling point go up. So this one's always going to be the lowest. Just like freezing point depression, the highest freezing point is going to be the pure water because all of the other ones are going to make the freezing point lower. So then the question really becomes how many particles or pieces are dissolved in the water. So what I'm going to do is I'm going to think about how many moles first, and then I'm going to consider the Van't Hoff factor later on just to sort of make sure, I guess, what's going on. So for HCl, I'm going to take 7.0 grams times 1 mole over 36.45 grams. So that's just the molar mass of HCl. equals 0.192 moles. I'll do the same thing for sucrose. Sucrose, 7.0 grams times 1 mole over the molar mass of sucrose, which is much bigger, 342.34. So this equals 0.0204 moles. And then I'll do the same thing for glucose, 7.0 grams times 1 mole over, for glucose, the molar mass is 180.18 grams, and we should end up with 0.0388 moles. So from this point, now we're going to sort of have to think about, well, how many particles are going to be, and how is that going to affect the freezing point? Right away, I can see that this has the most number of moles. The HCl has the most number of moles. This number is way bigger than these two numbers over here. And I also know that the Van Hoff factor for HCl is going to be 2. So it's actually going to split into 2 times this number of moles of pieces. So HCl is for sure going to be the substance with the lowest freezing point, and likewise, it's going to have the highest boiling point. You're going to notice a pattern with how these numbers correlate to one another. Now for sucrose, the Van Hoff factor for both sucrose and glucose is 1. So I'm just going to do a direct comparison for the number of moles. Sucrose has less moles, as the least amount of moles out of all of these. So sucrose is actually going to be 3, and then glucose will be 2. So again, basically I'm ranking these from number 1 is going to have the most number of particles. So this is our question: how many particles are dissolved in the water? So hydrochloric acid has the most number of moles. It also has a Van Hoff factor of 2. So it's going to have the most number of particles. It's going to have the lowest freezing point. It's also going to have the highest boiling point. Next is going to be glucose. It's got a bigger number of moles than sucrose. Van Hoff factor is 1 for both of those. So glucose will be next, and then sucrose will be after that. And then the pure water, of course, like we said earlier, that's going to have the highest freezing point and the lowest boiling point. Over here, it's just going to be the opposite. This is going to be 2, and this is going to be 3, right? So again, we could go through that. Number 4, the one with the highest boiling point, is going to be the one with the most number of moles, most number of particles. The next highest one will be glucose, next highest number of moles, considering the Van Hoff factor as well. Next would be sucrose, and then finally our pure water is going to have the lowest boiling point. Let's do one more example that gets into a few more of the Van Hoff factor issues, I guess. So here we've got the same exact thing. Right away, I guess we could say this is going to be 4, this is going to be 1. We know that because the way that our freezing point, depression, boiling point, elevation works. So let's go ahead and figure out for each one of these. For KNO3, we've got 8.6 grams times 1 mole over the molar mass of KNO3, which is 101.11 grams. That equals 0.0850 moles. For glucose, make sure that we can see this, we've got 8.6 grams times 1 mole over, so for glucose it's 180.18, same as the other side, and that should equal 0.0477 moles. And then lastly, our calcium chloride, that's going to be 8.6 grams times 1 mole over 110.98 grams. And for calcium chloride, we're going to end up with 0.0775 moles. Okay, now for each one of these, we also need to be taking into account the Van Hoff factor. So you might look at this and say, oh, well, I'll just organize these just like we did previously. This is the most number of moles, this is the least number of moles, but we need to take into account the Van Hoff factor. So KNO3, we need to be able to identify that this is an ionic compound that's going to break into 2 pieces. The I value for KNO3, the Van Hoff factor is going to be 2, and the Van Hoff factor for calcium chloride is going to be 3. And I guess the way that I know that, I recognize NO3 as a polyatomic ion. NO3 is going to have a -1 charge. I notice potassium is a metal, so I would know that potassium, it's in group 1. It's going to have a +1 charge in an ionic compound. So it's going to be +1 with a -1, Van Hoff factor of 2. Calcium chloride, calcium dichloride. It's got a calcium, I guess we don't have to say dichloride, but just calcium chloride. It's got calcium with a 2+ charge. Calcium is in group 2. So in an ionic compound, it's going to form a 2+ charge. And then I've got 2 Cl minuses, so this would have a Van Hoff factor of 3. If this is not making sense, the Van Hoff factors, then definitely we need to take a step back and make sure that we understand, where we're getting those that goes way back, to general chemistry 1 to figure out what our ions are breaking into. But anyhow, so we could sort of think of this number of moles. And then really, if we think about our equations, delta TF equals KF times molality times I, we're going to be multiplying this number of moles by our Van Hoff factors. So for potassium nitrate, our Van Hoff factor is 2, but for calcium chloride, our Van Hoff factor is 3. So even though this is the most number of moles, because we've got different Van Hoff factors, calcium chloride is actually going to be the one that's going to have the biggest effect. It's going to be the lowest freezing point. It's going to be the highest boiling point because I've got an intermediate number of moles, but if I take 0.0775 times 3, then that's going to, make it so there's more particles, right? Always remember what's the goal here? How many particles are dissolved? That's the question that we should be asking ourselves. Since the calcium chloride is going to break into 3 pieces, we're going to have more particles, so that one's going to have the biggest effect. So that's going to be our lowest freezing and our highest boiling. Next is going to be the KNO3, so we've got more moles than our glucose, and we've got Van Hoff factor of 2. But this, calculation does not add up to as much as the calcium chloride. So then our next one would be the KNO3, so that's going to be a 2. It's going to be a 3 for our boiling point, and then obviously this must be the other numbers there. So hopefully that makes sense. Really we need to think about this equation, how many moles of each substance we have, what the Van Hoff factor is. We need to take all those things into account. The freezing point is always going to go down. The boiling point is always going to go up. A lot going on in this topic. All right, hope that helps.